Hello everyone. This hands-on GeoGebra workshop aims to give you an overview of the skills in using the mathematical software GeoGebra. For this workshop, the graphing mode in Calculator Suite of GeoGebra will be used to demonstrate some essential functionalities. So hope you can be better equipped to use GeoGebra for economic analysis after watching this video. In the first part, we will focus on the simpler functionalities, such as the intersect and midpoint or center tools, as well as the line and segment functions. For most functionalities, they can be found in the Tools section on the left-hand side panel here. To begin with, the point or intersect function can usually help us to locate the intersection point between the two lines. For example, if we want to find the x and y intercept of the straight line y equals to 100 minus 2x in GeoGebra, we can use the point or the intersect function. What you need to do is just to collect the intersection point between the straight line and the x-axis in order to find the x-intercept. Equivalently, we are going to collect the intersection point between the straight line and the y-axis to find the y-intercept of the straight line. This result is quickly shown in the algebra panel here. Additionally, if we wish to find the midpoint of two particular points, then the midpoint or center function will be useful. So click Tools, scroll down and find something called midpoint or center under Construct. Just click the 2 points on the plane to obtain the corresponding midpoint. And as you can see, point C will be the midpoint of AB. The coordinates is also shown on the algebra panel here. Right? In addition, we have the line and segment functions that can be used when 2 points are given. As the name suggests, the line function can be used to construct a line passing 2 particular points, whereas the segment function can be used to construct a line segment with 2 points at the endpoints. Say if we have 2 points here, 2, 8, and 6, 4. Okay, just some random points on the coordinate plane here. So what happens if we apply the line function on these 2 points? So let's find the line function first. Click Tools and then scroll down to find something called line. Okay. If you click points A and point B, then GeoGebra would give the straight line and the equation passing these 2 points, as you can see. Alternatively, if we are using the segment function, we can obtain the line segment with these points A and B as the endpoint. The segment function is located next to the line function. Although the line function and the segment function look similar in some sense, they can actually be utilized in different settings. In the following, we'll discuss some problem sets that allow us to make use of these functionalities that have been introduced in the first part of this workshop. So the first question is about the revenue maximization under a linear demand curve. In the question description, we have 2 price quantity pairs of chicken rice, and we are going to find the revenue maximizing price and quantity of chicken rice here. Our goal is to derive a linear demand curve with the given 2 points, and then find the midpoint along this demand, since the midpoint of the demand curve would give the revenue maximizing point. So let's type the 2 points in GeoGebra first. At the quantity of 1,110 the corresponding price is 65. So this is the first point. Whereas at the quantity of 1,100, the corresponding price is 67. So we have the second point here. Right. Since we already had 2 points on the straight line, we can now use the line function to derive the linear demand curve. Click Tools and then find the line function. What you need to do is just to collect 2 points A and B. Then GeoGebra will help you plot the straight line passing these 2 points, which is also the linear demand curve in question. After that, how can we find the revenue maximizing point, which is also the midpoint of the demand curve? We can actually locate the x and y intercepts of this linear demand curve first. So using the intersect function, point C as the x-intercept and point D as the y-intercept. Then we can use the midpoint or center function to find the midpoint of CD, or equivalently, the midpoint of the linear demand curve. So point E will be giving us the revenue maximizing point. The corresponding x-coordinate would be the revenue maximizing quantity of chicken rice, 717.5, whereas the y-coordinate of point E would give the revenue maximizing price of chicken rice, 143.5. Okay, so let's move on to the next question for demonstration. So it will be about trading in a closed economy, where we have the productivity of Tony and Nick given this question, and they have a desired consumption ratio. Scandal to dress is in a ratio of 1:1. What would be the optimal production of scandals and dress in this case? And so I suppose it is clear to you that Tony has the comparative advantage in producing dress, while Nick has the comparative advantage in producing scandals. You may actually construct an opportunity cost table yourself to check, but here I'm going to focus more on the use of GeoGebra functionalities with you. And to deal with this kind of problem in a closed economy, there are 4 guided steps that I have outlined in the PowerPoint slide and also put down here on the right-hand side so that you can better follow what I'm trying to deliver. In the following demonstration, I will plot scandals on the x-axis and dress on the y-axis. Now, the first step is to put down the x and y intercepts of the joint PPC by adding the maximum amounts they can jointly produce. So the x-intercept simply means that if they only produce scandals, what will be the total amount of scandals that they can produce? It would be 107 plus 36. So this is the x-intercept. On the other hand, the y-intercept of their joint PPC simply means that if they only produce dress, what will be the total amount of dress that can be produced? So the y-intercept would be 107 plus k. By the way, no worries. So you can just directly type the unknown k in GeoGebra. At the end, you will realize that the value of k doesn't affect the result anyways, as far as the value of k is smaller than 36. So this is step 1. Step 2, to find the king point of the joint PPC, which is also the point of complete specialization. So at this king point, Nick will be producing 36 scandals, and Tony will be producing 107 units of dress. So 36, 107 will be the king point. Again, you may check this on your own by constructing an opportunity cost table. Step 3 is to use the segment function in order to derive the joint PPC. Okay, so find the segment function to derive the joint PPC. The key is that if we can find a point on the joint PPC such that it attains the desired consumption ratio of 1:1, then it will be the answer to this problem. So this is why we'll move on to step 4 to find the intersection between the desired ratio 1:1 and the joint PPC. Okay. To illustrate the desired consumption ratio of 1:1, it will be given by the equation y equals to x. So the intersection point will give us the result. So as you have experienced, after this series of procedure, we can obtain the optimal production of scandals and dresses, 71.5 units for each of the good. Right. In the second part of this workshop, I would like to walk you through the use of the Polygon function. So this tool is very useful when you're required to find the area of some regions. As an example, let me just randomly put 3 points on the coordinate plane here. If you wish to find the area of this triangle ABC, we can simply utilize the Polygon function to do so. So scroll down and click More, and then there will be something called Polygon. So to make use of the Polygon function in finding the area of some regions, what you need to do is to select the vertices of the region and then end with the first point that you have started. With that, the value of the area is shown on the algebra panel here, 2,193 point something. Second of all, the construction of dependent objects is also convenient in problem solving. Imagine we have a point, pi here, or 3.1415, blah, blah, blah here. How can we draw a vertical line passing through this point? Shall we type x equals to 3.1415, blah, blah, blah on the algebra panel? Personally speaking, I do not recommend this approach, as this might incur some rounding errors and other kinds of trouble. A smarter way to tackle this is to type x equals to x bracket a in the algebra panel, where a is the name of the point, pi. As you can see, we have the vertical line passing through point A. X bracket A returns the x-coordinate of point A, which is exactly what we wish to construct. Similarly, if we want to draw a horizontal line passing through the point pi, then we just type y equals to y bracket A would do. This is because y bracket A would return the y-coordinate of point A. So let's go through a problem to understand how we can use these functionalities. So I have this question about the demand and supply. So let's see. So we have two groups of consumers, A and B, for the good. And we are going to find the welfare loss if the central planner forces the economy to reduce production of good X by 50% of the market equilibrium level. Okay. So to start with, let's derive the combined demand curve first, because we have two groups of consumers. So let's type the individual demand and also to derive the combined demand curve in question. Okay, so these are the individual demand curves. How can you derive the combined demand curve? When the price is low enough, specifically lower than 677, then both groups A and B are willing to buy positive units of good X. So this is why the combined demand at price lower than 677 will simply be the sum of the individual demand of two groups. Okay. However, remember, the combined demand curve here is kink because when the price is higher than 677, Group A consumers are not going to buy positive units, but only Group B does. So this is why we will take only the individual demand expression for Group B to represent the market demand curve when the price is higher than 677. Okay, so to conclude, when the price is high, we take the blue portion as the market demand, whereas when the price is low, then we take the red portion. Okay, so to better understand the position of the market demand curve, we can refer to my drawings at the bottom right-hand side here. Next, because we need to find the market equilibrium point first, let me also put down the market supply curve. Therefore, here, the intersection point, point A, will be giving us the market equilibrium point. How can we reflect the reduction in output by half in GeoGebra? We can do this by typing x equals to x bracket A divided by 2, where the right-hand side would be the half of the market equilibrium quantity. This is the new quantity after the reduction in output. As the final step, the deadweight loss is simply the unattained total economic surplus compared to the market equilibrium level. So we can make use of the Polygon function to help us find the area of the welfare loss. Now we can obtain the result on the algebra panel as the required welfare loss. Moving on to the third part of this workshop, we are going to discuss the use of the slider function. The slider allows us to incorporate an unknown number into some equations for calculations. So you can see that I actually implicitly use the slider function in the problem about power of trade just now. You can either access the slider function through the tools section, here is to access the slider function via the tool section. Or you can also directly type something in the algebra panel like this. So let me plot a straight line with K, the slider thing here, as the y-intercept for better demonstration. Okay, so as the value of K changes, the equation of this straight line changes. In addition, if you would like to change the bounds of this slider, you can click three dots and then settings. Finally, press slider and you should be able to see a place for changing the minimum and the maximum input of the number K. Okay, so that's it. And again, I will move on to discussion of a problem stats. So for this question, it is dealing with a long-run quality adjustment due to an effective price ceiling. So this is involving a concept in Chapter 7. In case you have not learned this topic in Econ 1210 yet, you may skip this problem first and to watch it afterwards. So no worries, we still have other questions to demonstrate the slider function, which is to solve problems about taxation and subsidization. So it will be the next question to be discussed. Anyway, To start with, let me type the demand and supply functions in GeoGebra first. Right here. So we have a price ceiling at $100 and is effective as well. In this question, we will utilize the slider function to do some trial and error in order to solve the problem. So let's first create a slider number k and adjust the bounds accordingly. Okay. Since seller's production cost for each bottle of vodka is reduced by $k, then the supply will increase, shifting downwards by $k. At the same time, buyer's willingness to pay is reduced by $2k per bottle of vodka. The demand would decrease, shifting downwards by $2k. So we have derived the new demand and new supply due to the quality adjustment. In the long run, we know that the new demand and new supply would adjust until the point where they intersect at the original price ceiling of $100. Hence, we can just let GeoGebra to play itself until the point where they intersect the original price ceiling of $100. So at this point, it will be the new market equilibrium, point A, and we have successfully found out the market equilibrium price, 100, at the original price ceiling, whereas for the market equilibrium quantity, 50 units. All right, so we'll move on to the next problem using the slider function to solve the question about the subsidy expenditure target. To start with, let me type the demand and supply functions here first. All right, like this. For this problem, we are going to use a trial and error approach to find the per unit subsidy that can achieve the target subsidy expenditure of $5,500. And this will be the market equilibrium point. To begin with, let me create a slider that represents the new quantity after subsidization and call it x equals to k, where k is the slider. Next, I will adjust the lower bound and upper bound of the slider. For the minimum, I just type it slightly greater than the market equilibrium quantity. All right, somewhere like this. A question here for you. What is the area of subsidy expenditure from the diagram? It is actually the rectangle shown here as the subsidy expenditure if we have a per unit subsidy of this amount. Therefore, the objective is to draw a rectangle using the Polygon function here such that we can move the slider and observe the target subsidy expenditure. Specifically, I'll use the Intersect function to locate the subsidy wedge first. And then draw the two horizontal lines passing through the points B and C. So using a Polygon function, the area of subsidy expenditure is represented by this rectangle. the power of the slider function can be exhibited here now. We can move the slider. So we can move the slider and to conduct the trial and error and see at what level of quantity the subsidy expenditure can attain the desired target $5,500. As you can see, the area of the subsidy expenditure would change continuously. As you can see, it is now closer and closer to the target, 5,500. When the subsidy expenditure now reaches to a value close to the desired target, you can just eventually type the numbers to test. You need to get an even smaller number. Okay, closer and closer. Oh, okay, smaller than the desired target. So as you can see, the new quantity will be between 3,082 and 3,083 to attain the desired target, 5,500 of subsidy expenditure. So you can further do a little bit of trial and error. Right now, it is already quite close to the target 5,500, and we can accept the result here. So the desired per unit subsidy is simply the vertical distance between points B and C. It will be 4.6422 minus 2.8578. You can do a little bit of calculation in the algebra panel here to calculate the result. It will simply be y bracket B minus y bracket C, the y coordinate of point B minus the y coordinate of point C. Okay, so the desired per unit subsidy will be $1.78. This is how we can make use of the slider function to conduct certain kind of trial and error in GeoGebra as an alternative experimental approach to solve the target type question. After talking about the functionalities in the tool section, we will instead look into a more general feature. So for any kind of functions we plot in GeoGebra, including a cubic function that I'm trying to type here. Okay. We can actually make use of the special point thing here. GeoGebra would then return some special points like the x-intercept, the y-intercept, or the turning points of the graph here. Some of these points may be quite useful in calculations. So I will demonstrate how we can make use of the special point feature with this example of maximizing tax revenue. As the marginal cost of alcohol is constant at $350 per bottle, then the supply curve is actually horizontal and perfectly elastic. This means that when there's a per unit tax of $T, then the price paid by buyers will become 350 plus T accordingly. The whole tax burden will be shifted to the buyers. Thus, the after-tax quantity will simply be the corresponding quantity from the demand curve at the price of 350 plus T. By plotting the graph of tax revenue function in GeoGebra, we can save the effort of finding the simplified form of the tax revenue expression. How can I do that? Since total tax revenue is the per unit tax of $T multiplied by this after-tax quantity, so this is why I have the tax revenue function as this complicated thing. So we can type this thing in GeoGebra and replace the per unit tax T by the variable X. After all, you will be able to obtain a quadratic function, and there will be a maximum point of it. You just need to click the special points after the three dots. Then we can have the maximum point that gives the problem to this question. When the per unit tax is $63, then the tax revenue of the government is maximized. Apart from plotting graphs of functions in the algebra panel, we can in fact carry out some simple calculations here in GeoGebra. Suppose we need to calculate the elasticity of demand at the equilibrium point, given by the demand and supply functions here. At the beginning, of course, we need to find the market equilibrium point and can make use of the intersect function. As a recall, to calculate the elasticity of demand, it will be delta Q divided by delta P times P over Q. For the first fraction, delta Q over delta P, it is simply 1 over the slope of the demand curve. And we have the slope of the demand as -2 here. So the first fraction is 1 divided by -2. While for the second fraction, P over Q, equilibrium price divided by equilibrium quantity, we can make reference to point A to calculate the price divided by quantity, which is Y bracket A divided by X bracket A, because Y bracket A returns the Y coordinate of point A and X bracket A returns the X coordinate of point A. As a result, we have the elasticity of demand at the market equilibrium point calculated in GeoGebra, -1.25. As the final note in this GeoGebra workshop, I wish to conclude by giving some tips regarding some basic settings. First, you're recommended to change the settings in GeoGebra so that more decimal places are displayed. The change of decimal places can be done by clicking the setting icon right here, and then settings again. Finally, the second icon for global. You can see the setting of the rounding of numbers here. So showing more decimal places is very crucial, especially when the values are only the intermediate results. If you only use 2 decimal places in your earlier results, then the following calculations based on these values may incur large rounding errors. So this is the first tip. Second, sometimes it may be hard to observe the true shape of the curves with strange scales. Suppose we have these 3 demand curves, okay, which are actually very flat. And we basically cannot see that they are downward sloping. Consequently, we may want to adjust the ratio of the plane to accommodate for that. This can be done by right-click the plane to choose Zoom to Fit. As you can see, now at least you can observe the downward sloping behavior of the demand curves. In case this method does not work, you may instead change the ratio in the setting icons here. Either way will work, using the Zoom to Fit thing, or to change the ratio on your own manually in the setting icon. Third, some students would like to change the colors of the curves to better visualize them in the graph. Like the 3 demand curves here again, they are very close to each other and you may mix them up together easily. If you'd like to change the colors for these 3 curves for better visualization, click the 3 dots and then choose Settings. You can see something called Color, and you can change the colors here easily. That's pretty much the things I would like to highlight in this workshop. Hope all the content here would give you a hands-on experience in using GeoGebra and an opportunity to master this software. Thank you very much for going over this workshop materials.